Okay, so we're going to move on to API resolution. Okay, so when you're writing running a C++ application or .NET application of some sort, Windows comes preloaded with a bunch of dynamic libraries, and they also come with static copies of the libraries. So your compiler is going to have the static libraries available, so you can either choose to use the dynamic libraries and load functions on the fly, or you can choose to build them into your application. And what you'll see here is you got this include windows.h, so it's kind of a catch-all for all libraries, or some of the standard API functions that you're going to need when you're building a Windows application. And then you'll have some sort of a call to something like this: create file. It takes a file path. It takes some sort of options about whether you want to read or write, and so on. So there are several ways of doing this, and in this situation, we are completely relying on the loader. Okay, so we're expecting the compiler to know where to get this API, and when we launch our application, Windows is going to do some magic, read the headers of the application, and then it's going to make that API call available to you, so you can actually create a file in the file system. So, and that's done in the background with these functions load library and get proc address. So load library says go get a DLL. It's got to be somewhere in the search path, which is generally the system32 directory, the Windows directory, the current directory, and anything else that you specify as a directory that can be used for the load path. So the next possibility is that you do a manual load. So in this case, I've defined some sort of a pointer to an API call, and then I actually go out and call load library myself. I say I want user32.dll because it contains my function message box, and then I call this p message box. Or I create this p message box, which is going to be a pointer to the return value of this get proc address. So, oops. I assigned huser32 to the return of this load library. And what that actually is, this h module, is actually the base address of user32.dll. So this way the application knows where to find the beginning of the library. And then get proc address uses that as a starting point to search for message box A. And it literally searches for that string within the headers of our users32.dll file.
If it's a standard library and you don't want to give away what function you are going to call, can you just, if you know the address, can you just call directly to the address of that function?
Okay, that's a good question. So I talked briefly about return to libc attacks this morning, and that's something that is has become more complicated. It's more of a challenge to do these sort of attacks, and that's because you can't necessarily rely on a function being at a particular address anymore. At one point, yes, you could say the library is most likely, or the API is likely to be at this particular address because the behavior of the loader was predictable. But even that's not always the case. So when your application, or when the Windows loader tries to bring a file into memory, it tries to find, it determines first of all whether it needs to be loaded in a very specific address. So you could actually build your program and say, my program has to be at address 012345. Now it actually has to be page aligned, so you couldn't use that exact address, but so a page is generally 4K. So you have to be aligned on some boundary of 4K, like 0 or hex 1000, 1000. So it's generally not feasible to reference an API directly using its address. Generally, you have to find it somehow. So the other possibility is sort of a hunt peck method. Okay, so there's still some predictable behavior of the Windows loader, because at some point you have to do things consistently so that the programs have some expectation of how they can get the code that they need. So first of all, you have to locate the structure called the PEB. Okay, and so this is the process environment block, and it refers to it is referred to, sorry, in the TEB. Okay, the PEB is a process environment block. The TEB is the thread environment block. So your application has a way of finding this TEB, thread environment block. So processes run multiple threads to be able to do multiple jobs at the same time. So each running thread has to have this information about its environment. Okay. So we've got this environment pointer, and we've got this PEB, and the PEB gives higher level information about the application running. So each thread can kind of be able to communicate with its parent or know something about its parent. So in this situation here, we've got an assembly instruction XOR EAX, which sets EAX to 0. Okay, and then we reference FS EAX plus 30, which really turns out to be FS X30. So this is the standard location for the, so FS0 is the standard location for the TEB, and 30 is the offset to find this PEB item, okay? So Microsoft explicitly states that you can't expect this structure to stay this way until the end of time. So this is not an official way of getting a library. Okay, this is the hacker's way of getting a library. But it has been reliable for years and years and years. It's been going on for the last decade. And so we can expect that the PEB is located at 30 bytes from the beginning of the TEB. The TEB is always accessible from FS, the FS register. It's at the base of the FS register. So if you don't remember from previous classes, the FS register is a frame segment register. And so segment registers are commonly used in Unix systems to prevent, to keep permissions of different areas of memory. And Windows doesn't really care about this. It doesn't really worry about segments, but it does use the FS register. So definitely something you want to keep in mind. So once we've got this PEB, then we want to step through that, and it contains, it can lead us to information about all of the libraries that are contained, that are used by the current application, the running application. So at offset OC, or hex C, we've got this loader data, okay? And in this loader data, we have 3 different lists. We've got in load order, in memory order, and in initialization order module list, okay? Module list is a list of all the portable executable, the PE files that are loaded into this memory space. And that includes kernel32.dll, which contains a lot of stuff like a create file, for instance. It would potentially contain, well, it contains ntdll.dll, which is always the first thing to be loaded. And it turns out, as we'll find out in a little while, in Windows 7, there's actually a bridge. There's actually another library that's loaded that isn't loaded in Windows XP. So I'll come back to that. But for that reason, we're actually going to use a VM for our examples, and I'll walk through that soon. So in assembly, we're going to see this code that we just saw up above. It's not always going to look exactly like this, but in some way it's going to reference FS30. Okay? And then we've got removing the value at this C, the offset C, from our PEB object. So EAX is now PEB, and we get offset C from it, and get what's located at that address. Store that in the EAX. And then we get this 1C, okay? In initialization order module list is located at offset 1C from this PEB loader data item. And then this loads the instruction. What that does is it takes the value in ESI and then loads the value located there into ESI. So it's basically, this is a quick way of traversing a list if the list pointers point to each other, okay? So basically this is a way of stepping through this order, or this list, this module list, in the order that it's loaded. And what is predictable is that ntdll is loaded first, and in Windows XP, kernel32 is loaded second. Okay. Now in Windows 7 it's different. There's actually one that's loaded in between the two, and I'll demonstrate that later. Then this last instruction here, grab the module base address. Okay. What this is doing is getting the location of kernel32.dll, and we can then use that to find functions that are contained in kernel32. So what happens next is in a Windows executable, you have headers, okay? So at the beginning, you have this thing called a DOS header. And the first 2 bytes of that are MZ.
Would you please adjust the camera, please?
This thing. Okay, then commonly you have some, so in this DOS header you usually see something that says, this is not a DOS application or something like that, a very common string. And then you have these NT headers. And the NT headers are referred to by the DOS headers. At the bottom of these NT headers, there's a directory. And in that directory is a bunch of information about where to find debugging information, export information, and most importantly, import information for our application. Okay? So that directory is going to contain a relative address from the base to imports. And the imports table is just a whole bunch of integers, pointers, to the various different functions that you want to use, whether it's create file, receive, send. And then there are also the exports. And you're going to find this within DLLs, okay? So what we do here is we get the DOS, we have the base address, we have this address as kernel 32. That's what we figured out using that previous method, okay? Then from the DOS header, we know how to get to the NT headers. It's a reliable offset. It's always at hex 3C. Then we get these NT headers, and once again, a reliable offset to the export directory, which gives you a pointer to this guy. And then we have the exports. And the exports contains basically just a list of all the function names. So if you actually open up in a hex editor your executable, you'll actually see every function that you expect to be available from that library. So what this hunt and peck method does is it creates a hash. So it creates some integer representation of the string that they're looking for. And then they embed that function, the function to calculate that hash, into their, say, shellcode or whatever. And then that's used to go through every item in the exports directory, every integer, or every string, sorry. And it calculates a hash for each one of the names until it finds a match with the one it's looking for. Okay. Once it finds that match, it's going to go ahead and use more information within the export. So the other information that's contained in the exports, aside from the names, is the actual address or the offset of the function. Okay, and that offset's going to be from the beginning. So we get some value out of here, and then we add it to this base. And from there, we'll have the address of the function we're interested in. So the last thing we do is retrieve that function pointer, and then we use that. So in the code, you'll see something like this. So we've got this load instruction, and it is, at this point, we've already got the table of names. We're getting a pointer to a string.
So I was just kind of curious, why do they use a hash instead of just referencing it by name or the ordinal value?
Well, a couple reasons. First of all, this sort of thing was kind of started a little bit after SQL Slammer, or at least that's when it became widely used. And they were trying to jam shellcode into as small space as possible. Okay, so if you sent your shellcode out and it needed to get 15 different API calls, that's really going to add up in size of the strings, right? So you've got create file, you've got get temporary directory, you've got all these strings. Well, you can represent that in 4 bytes. Okay, now let's say you're trying to get 100 of these things. okay? At some point, you're going to exceed the size of this code that calculates a hash. So the size of the size of the hashing function plus the size of those integers, if that's smaller than the size of all your strings, then it's a better way to go. So partially for size, and it also somewhat obfuscates the meaning of your code, right? So if I get some sort of a packet and I see it's got all these API names in them, and this packet is just used to communicate with my database or whatever, there might be something that it might not appear kosher, right? It might appear like there's something wrong with this thing. And so I could potentially write a signature to say, okay, if I see kernel 32 and load library and create file and send and receive all in this packet, and those are things that I don't normally see, then I can write a signature to identify that.
Yeah, if you see an infection vector, you just detect it and tell the contact the intruder and whatever. Right. So you'd be able to see that.
Yep. And at that point, you can say, well, why don't I create a signature based on the hashes, right? Well, you can write whatever hashing algorithm you want. So, in a lot of cases, you'll see something like this. So this instruction right here is a rotate 13 bits, okay? And so a paper came out about this several years ago that described this algorithm. Then all of a sudden, lots of exploits started actually containing this code. So you'll actually see this out in the wild, whether or not it's still used today. Probably more so by your script kiddies or by people who don't quite frankly care if they're detected. So you still may see this today.
Just to clarify, when it says rotate EDX 13 bits to the right, does that mean bit shift 13 bits to the right, or what does it mean by rotate?
Yes, it is a bit shift. So
it is a right shift.
Right.
It is the double greater than expression.
Okay. So let's say we're going to rotate this thing 3 times to the right. So what I end up with is 1, 2, 0. So I started here. This is my new beginning. So I pushed these to the right. They came to the beginning. Okay. And then these guys right here, 1, 0, 1, 1, end up at the end. So that's the operation that's occurring.
Actually, I think bit shift right puts leading zeros at the very beginning.
Oh, that's shift. Okay, that's different than so you've got shift operations and you've got rotate.
Okay.
Okay, so shift is just going to lose the data. It's just going to push it off the end, whether you're going to the right or to the left. Rotate operation is actually going to maintain that information and move it to the beginning.
Okay.
Okay. So what you see happening here is we're actually loading. So currently ESI contains a pointer to the string, and this load speed instruction, it basically loads into AL, the low byte of the EAX register. It loads whatever is pointed to by ESI. It loads a single byte. Load SB, so load string B, or load string byte. Okay, so it's loading a particular byte out of a string into AL. Then we're checking to see if it's 0. Test AL, jump 0. So if it's 0, then we're going to leave this loop. If not, we're going to continue on. Or, well, in this case, it is. And then what we're going to do is take EDX. Now, EDX is what we call an accumulator. It actually contains the value of the hash that's been computed. It usually starts out at 0. We're going to rotate that accumulator, and then we're going to add EAX to EDX. So we're adding the information about the next byte of the string to our hash. So we do this in a loop, and we build up this hash. Bits get rotated around. So if the bits didn't get rotated, then all you'd have is a bunch of zeros followed by some value computed by EAX, because what we're adding to EDX, well, you'd have a low number is what I'm saying. So I want to actually demonstrate this to you. So why don't we take a little bit of a break? Do I have any questions, first of all? So you can go ahead and unzip labs.zip. And so I got a little hand wavy when talking about the headers. So, for instance, let's just take, for example, our bomb.exe. Okay, I've got this tool, CFF Explorer. Pretty handy tool for doing analysis on binaries. And you can see this gives us a nice little view of all the headers within bomb.exe. It's parsed everything else out nicely for us. And as I mentioned, there are DOS headers, NT headers, there are these directories, data directories. And so this guy doesn't have exports because it's an application, it doesn't export anything. But you can see here we've got, in the DOS headers, we've got this ELFA new. Okay, and this is what I was talking about, the offset 3C. It's telling us that at the offset D8, we have the NT headers. You can see at D8, here we've got a signature, followed by file header, optional header, and data directories. So all this stuff is contiguous, all this from the NT headers to the data directories, all that's contiguous in memory. And then you'll see export directory RVA, directory size. See, those are 0, so there's no export information. You can see we've got this import directory, and CFF Explorer tells us that that data is contained in the RData section. Then we can actually take a look at the import. So if we choose the import directory here, then we've got MSVCR 90.dll. It's common a Microsoft Visual Studio C runtime, and kernel 32.dll. And this contains a lot of very commonly used functions. Now this thing doesn't create any files. It doesn't do any network connectivity. So we don't see any of those sort of functions in here. But in other applications, you might see a lot of that. So that's CFF Explorer. Now, I gave you several different files here, and the first one we're going to take a look at is linked. Okay.
Hey Matthew, is it showing all the functions in that library, or just the ones it's using?
It is just showing the ones that it's using. So this application is actually using these functions. Well, at least it's loaded them into its memory space. It doesn't necessarily mean that they're called, but chances are the reason that they were put into these headers is because when this program was written, these functions were called. No problem. So if we look at, so does everybody have CFF Explorer? Okay, Okay, so if you haven't already launched it, go ahead and open it. I'm going to close my bomb.exe here. And we're just going to take linked.exe, we're going to drag it into CFF Explorer. And if we look at the imports here, we'll see it's got user32, msvcr90.dll, kernel 32. This one we didn't see in the last one. We can see message box, so we can expect that there's probably going to be some sort of a pop-up at some point. Maybe, maybe it's conditional on how we run the thing. Now, if I just go ahead and launch linked.exe, you get this little pop-up here. The message box function was loaded at link time. So this was the first example. So in the wiki here, this is this relying on the loader. So this function was actually, or this application was actually written kind of like this, where instead of create file, we've got the message box function directly called, and it was just made available to the application through this header, this windows.h. So I'm going to go ahead and close the bomb lab and go ahead and open up IDA or close the bomb lab if you already have it open. And we're going to go ahead and load linked.exe into our application here, into IDA. And I'm going to go ahead and use the defaults. And you can see this is a very simple application. It doesn't even have any calls aside from this call to message box. A lot of the magic is done behind the scenes to make message box available to us. And we just have a series of pushes. We've got our little preamble here, the prologue. We've got the exit of the function. And then we've got just this call, a series of pushes, call, message box, very simple. So very quickly you can figure out what's going on here. So I'm going to go ahead and close that. I don't care about saving it, so I'm going to say don't save. And I'll load manual load here. Now this one's a little bit more complicated. Still not a very taxing program to look at, but you can see we've got this call to load library, get proc address, so we're using user32. The return address of load library goes into EAX, and then the H module. H module is actually going to be used by our get proc address. See it's pushed, loaded into EAX, and then pushed onto the stack. So this is an example of the second example here, the manual load of an API, and this is actually some of the code that was used to write this. Okay, the last thing that happens here, you'll see, so get proc address, its return address, its return value goes into var4, and then we actually do this call. So this is, I talked about this a lot yesterday, and this is the first time I actually get to show it to you. So you see, we're getting a pointer to a function, and then we're calling that function indirectly. So there might be something else somewhere else in the application that sets var4. I could run this thing, debug it, and change what function is actually going to be called here just by changing this var4. So I'm done with that. And I'm not going to save it. Then we come to API search. And once again, we see strings that we recognize, users32.dll. This time, I don't have any information about which function is being called here. I see 5 different calls. One of these gets user32.dll, and that is an indirect call. So, you know, it might be a tip off right there. You see a DLL being passed to some indirect call. Very likely could be load library, but may not be the case. Could be some sort of file writing mechanism. Then we've got this function, which is called twice. And we've got this other indirect call here. Okay. So one thing you might notice is that you kind of get a call signature for before these indirect calls. You have a series of pushes, and then you have a call, and you have some idea of what the types of data that are actually being pushed onto the stack here. So these might be little hints as to what functions are actually being called indirectly here. And you'll also notice that before these indirect calls, so we've got this one here, we've got this one here. Before those calls, we have this call to this 401800. Okay. So let's take a look at that. So this is one of these things where when you've been looking at a lot of things that do this unpack method, you'll start to recognize 3C. Oh, I've seen that. 7, 8, 18, 20. These things are often used in conjunction with each other because, go back to the CFF Explorer. And I'll just demonstrate this. See right here, got offset 3C, okay. That corresponds to this 3C here. That's going to be ELFA new. That gives us E8, okay. And I know this is the NT headers, that's what ELFA points to. So that gets us to the base of this. Now, we've got this addition here. So we've got EBP plus EAX plus 78. So EBP contained whatever this argument is, whatever was passed to this function. And this is actually going to be the base. We're getting the offset, putting that into EAX, adding that to the base. Then we're adding another 7, 8, okay? So E8 plus 7, 8 is actually going to bring us to, so E8 plus 7, 8, if you do that math, it's going to turn out to be 160. It's going to bring us to this export directory RVA. Okay, so this value right here, and in our case, 0, is going to be stored into EDI. Then we're going to add, actually it's going to be, yes, stored in EDI. Then we add the base address to it. Now we have the location of the exports directory. Okay. And then from there, we're going to go ahead and traverse the exports directory. You'll notice down here we have the code that I discussed before. Got, at this point, ESI, through these instructions up here, they're going to get, this is walking through the names in the export directory. So I want to actually show you what that will look like. So I've opened up kernel 32 in CFF Explorer, and this time you'll see I actually have an export directory. And what this contains is this header block of information. It has three important arrays here. One's the address of functions, one's the address of names, and one's the address of ordinals. Okay. The function, the names is what we start out with. We're going to go through this list of names. That gives us an ordinal, which is an index into the function array, and the function eventually gives us an RVA. RVA is a relative virtual address. So in your memory space here in IDA, you see these addresses here. The RVA is going to be some offset from the base of this application, and this thing's actually loaded at 400000. Okay, so an RVA is actually from that base. Now the reason why IDA starts out at 401000 is because it's hiding away the headers from you. You could actually ask IDA to load that information for you, but in this case, IDA decides you don't really need to see the headers. You could probably use some other tool to handle it better anyways. IDA's not going to give you some organized view of the headers, so by default, it starts out just after the headers in memory. Okay. So these relative virtual addresses are going to be added to that base of the application in memory to figure out the actual address of the function. So what I'd like you to do is, I've got a file called dropper.exe. Okay. Now, in order to take a look at this thing, we actually need to use a virtual machine, because the way this behaves in Windows XP, it'll actually run properly. In Windows 7, I'll demonstrate after you've worked on this for a while why we're gonna have different behavior, and it's not actually gonna perform properly. It's not going to do what we expect it to do. So let's, has everybody changed their permissions on the VM itself? Everybody online, do you have the virtual machine? How about just no's? Anybody that hasn't found it?
I didn't see any no's.
Okay, good. In that case, go ahead and open up VMware. of the VM. So File, Open, and choose our desktop. Click on the Windows XP Professional directory, and then click on the VMX file. It'll take a second to load. It's going to ask if you want to take ownership. Yes, you do. And it's saying that because I have it open already. So does everybody have the VM open? Okay, once you go ahead and boot this thing up, you're gonna have to log in. The credentials for the VM are gonna be.
I moved it, I copied it. Or this virtual machine might have been moved or copied.
Okay, if you get that, just say it was copied. Okay.
I didn't prompt to take ownership.
It didn't?
No.
That's okay. As long as you're able to boot it. Okay. Now before we make this full screen or get all these options out of our way, we're going to add a share folder. So
What are the credentials again?
they're over there.
Okay, those.
So we're going to add a share folder so we can copy in our application. Click on the VM menu and then click Settings or hit Control D. And then you want to go to the Options tab. Is everybody with me? So once you're in the Options tab, you want to click on the Shared Folders item. It's the third one down. And I've already done this, but you want to change it from Disabled to Always Enabled. And I want you to click Add. Browse to the path where you stored the the dropper.exe file.
Oh, now it's at this.
In my case, I saved it on the desktop in the RE folder.
Should turn him down a little bit.
And
We'll call that
you can give it a name if you want.
We'll call that number 1. Well, there's adjustments on the.
And then click Next. And enable the share. Finish. So by now you should have a share folder. You should be logged in. And I'll catch up to you here. Now, I'm going to enter full screen mode. It's the third button here. Third from the left, that is. So now we want to get that dropper.exe. It's contained in, well, if you go to My Network Places from the Start menu, shared folders on VMware host, whatever you named the share folder, and let's get dropper.exe. Everybody with me? Anybody still trying to do this? You're welcome to use the debugger in this exercise if you want. If you have any questions about the debugger, let me know. So who's run this? Okay. What did you find?
Nothing.
Nothing.
If you get it input, it pops up a notepad window that says these are not the bytes you're looking for.
Okay. So it takes input. So it might be handy to have your command line available. So if I change into my desktop here where I have the file, and I run it, nothing happens, but if I type something, I give it one argument and it says these are not the bytes that you're looking for.
Matthew, you there?
I'm here.
I found a string in the RData section I was interested in, and I thought I could use the X to go back and see where it was referenced in the code, but it doesn't seem to be an option within IDA. Is that not how it works?
Okay, hold on 1 second. So, oh, okay. So you're trying to use the jump to xrefs.
Exactly.
Okay. Well, X is based on whatever line of code you selected. So if I hit X on, so if you got my window up here, I've got this D word here. I press X over that, and that tells me all the places it's used.
Okay.
But if you're looking for a particular string, then in that case, you're going to actually want to use the strings window.
That's where I was. That's where I was trying to use X.
Ah, okay. Okay. So let's take a look at the strings.
Was
So let's
actually
say-
looking at create file A.
So let's say we want to look at this bytes string, for instance. I can go to it by double-clicking it. Okay. And then once I go to it, so you see bytes here. I've got this A bytes, which is the variable name that represents bytes. Click on that. Then if I press X, I can see where it's referenced. Okay, so you actually want to, in the strings window, choose, double-click on the string that you're interested in, choose the variable name, press X, and you'll see this is pushed at this location here. Does that clarify things?
Sort of. I don't get a variable name when I double-click on the string that I was looking at.
Okay, so what string is it?
Create file A?
Create file A, okay. So the reason is this is actually an import. Okay, so in the RData section, there's actually this import table. It's the thing that's pointed to by the headers data directory.
Right.
Okay, and so this is only used at load time. So although I could define this as a string. So if I click on the first character, the C of create, hit A, now I have a variable name. But because it's not referenced at all, when I press X, it says there are no xrefs. So that's because this isn't actually used within the code. It's actually used by the loader.
Okay. Yeah, shoot,
So-
I thought I found a shortcut to the interesting code section.
Well, there's another place. Well, the imports are actually in this imports window. Okay, see how I've got create file A here?
Yes.
Try that.
Ah, okay. Thanks.